Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called Oil and Gas Industries Enterprise-Wide Optimization, Oil and Oil Products Blending. To provide these services, HI is supported by its business partners, GAMS, IBM and TD SYNNEX, all of which are producers of artificial intelligence technologies. HI is a company at the forefront of high-performance artificial intelligence. Oil Supply Chain Optimization. The oil industry includes global processes of exploration, extraction, refining, transportation and marketing of petroleum products. The largest volume products in the industry are fuels, natural gas, fuel oil, and gasoline. However, petroleum is the raw material for many chemicals, including pharmaceuticals, solvents, fertilizers, pesticides and plastics. The table, elaborated by IBM, shows a resume of the optimization solutions for oil and gas enterprises. Oil Enterprise-Wide Optimization integrates mathematical models for each of the links in the oil supply chain, in such a way to management the planning of the supply chain with a holistic vision. The design of HI Oil AWO was the result of work done for a multi-business oil company. The union of models, and their coordination, forms the hypothalamus of an oil enterprise. The current computational power allows to model detailed the supply chain, considering individually all the systems that compose it. This allows to visualize all the existing bottlenecks, and that affect the maximization of economic gains. Optimization solutions in the transport chain of petroleum products can be classified by their hierarchy, strategic, tactics, and operating. Several of these applications will be discussed below. The oil products mix for sell in the final markets. Optimizing the blend of crude oil and petroleum products is a multi-million-dollar application. It can be coupled to the production of oil fields, in such a way as to establish optimal plans for production, distribution, export and import. In addition, blending processes extend to petroleum products, for example, lubricants. It can be coupled to the production of oil fields, in such a way as to establish optimal plans for production, distribution, export and import. In addition, blending processes extend to petroleum products, for example, lubricants. Oil transport, trading and blending optimization corresponds to a dynamic model that optimizes oil distribution between fields, refineries and ports, the oil mix for use in refineries, the mixture of oil for export in accordance with quality standards and established supply contracts, import of oil according to offers in the spot global oil market, and import/export of oil according to offers in the oil derivatives financial instruments. The problem discussed in this section focuses on the distribution and blending of oil produced in the fields, to be distributed to the terminals of the oil facilities, where it will be delivered for use in refineries, own or in other markets. Refineries are modeled in an aggregate way, as an exogenous demand for oil. The model blend allows to plan transportation operations for multiple oil production systems, with a view to delivering crude oil blends to refineries, and/or ports, that are connected to the system. The system accepts any type of connectivity topology between facilities. The supply of oil is given through fields producing different types of crude oil, with a predefined availability. This offer can be defined dynamically, considering the evolution of the oil-producing fields' operations plans. It is also possible to consider buying crude oil in the spot market. The demand for commercial crudes occurs in refineries and export ports. It is possible to buy crude oil in the spot market, in order to mix them and obtain new commercial oils. It can also be considered purchases or sales of oil futures, which must be respected. The purpose of optimization is to determine the optimal operation of the system, in such a way as to maximize the utility produced, or to minimize the costs of satisfy a predefined demand. Integrally, the optimization process involves multiple crude oil blending processes, to make the optimal decisions related to the production, distribution, refining, consumption, and purchase and sale of oils over a planning horizon covering several periods. Two alternatives of modeling may be considered: the direct formulation of the blending process that generates nonlinear equations for short-term planning, and an alternative formulation that maintains the model linear, in exchange for increasing its dimensionality over time, for long-term planning. The fundamental hypothesis of modeling is that all installations are connected to transfer tanks, in which the oil is received, mixed and dispatched, to another terminal, or to an oil-producing, or consuming, facility. Linear modeling involves following the path of all oils that leave from a facility, and may pass through other facilities. In each installation, the product received is divided into oil for use in blending, and oil that is delivered to another installation. In the installations at the end of the path, whole product must be used for blending, or for attending the demand. A terminal can be conceptualized as a machine that takes multiple oil crudes, mixes them, and produces multiple blended crudes. The diagram presents the flow of materials in the petroleum system. The entities considered in the modeling are crude oil, oil field, oil terminal, tank, refinery, oil port, commercial oil, market, and regional market. Proof of concept: blending, transport, import, and export of crude oil. An example is the modeling of an integrated system of production, consumption, distribution, and purchase, or sale of blending oil. The features of this system are: oil is produced in the production fields, each field being characterized by the type of oil it produces. Such oil must enter the oil distribution system that feeds export ports, through which commercial commitments to sell oil in the spot market, or the financial markets, or directly to the refineries. Refineries must meet the need for crude oil based on the mixture of different crude oils, considering the technical characteristics of refineries. At export ports, oil must be dispatched to meet commercial commitments to sell oil. Associated with each sales contract are the physical chemical characteristics that must satisfy the oil delivered. In import ports, oil purchased through purchase contracts or by purchasing oil from the spot market, associated with each purchase, by contracts or the spot market, has the physical chemical composition of the oil bought. This very simple case considers 4 oil fields, 2 terminals of oil blending, 1 refinery, and 2 export ports, 1 to USA and 1 to Europe. The tables present the characteristics of the oils included in the modeling. The crudes produced in the fields have no commercial characteristics, are of many types, and their characteristics can vary throughout the planning horizon. Commercial crudes are standardized and are those that are traded in the oil markets. 2 cases were analyzed for static monthly planning of the petroleum system. No transfer limitations, unlimited transfer capacity between facilities, and with transfer limitations. The supply of crude oil in the fields is fixed exogenously. The image presents aggregated results of the scenario no transfer limitations. The image presents aggregated results of the scenario with transfer limitations. It can be noticed how production is activated in Refinery 1, due to the bottleneck generated by the transport capacity. In the real-life industrial processes is necessary to model chain blending processes. While a single blending process may be modeled linearly, by chaining multiple blending decisions the problem is complicated since it is not known a priori the characteristics of the physical chemical composition of the material resulting from a blending process that ends up being input of another blending process. This chaining of blending processes can occur in space, between multiple industrial installations, and over time, when the final stock of mixed products over a period becomes part of the initial inventory of the mixed product that is stored in an industrial facility to meet commitments in the future. The chained resulting problem gives rise to a nonlinear optimization problem. Next, a dynamic scenario is presented, in which the 5-month dispatch is simulated. The image presents the production of aggregate oil, and the prices of commercial oils in the different markets. The image presents the results of the moderate transfer limitations scenario. It can notice how the storage tanks are activated, and how the availability of oil is exhausted for the last period, this because the oil in the tanks is not valued at the end of the planning horizon. The image presents the results of the transfer limitations scenario, which due to the restrictions has more activity in the refinery and in the ports. The blend mathematical model can be adjusted to study the expansion of any of the facilities of the oil system. For this, binary variables must be included, and the constraints that represent investment logic. The case of expansion modeling is based on the previously used system. The possibility of building another oil blending terminal is considered. Since the expansion problem of an oil system corresponds to a strategic decision with long-term impact, the mathematical modeling indicated is stochastic optimization based on scenarios. In this case, at least two sources of uncertainty can be considered. First, the volume of oil that can be extracted from oil fields, when and how much. Secondly, the price and demand for crude oil in the final markets. Finally, when using stochastic optimization, it is convenient to include the analysis of financial risk to protect investments. This can be done by controlling risk indicators such as value at risk. Integrating crude supply, blending and product distribution models in refinery planning. Integrated optimization of the entire oil blending chain implies a holistic model of the problem. This vision produces greater economic gains than its piecemeal modeling. Crude oil blend optimization scheduling. This case is based on the paper. Crude oil blend scheduling optimization is an application with multi-million-dollar benefits. It can be coupled to the production of oil fields, in such a way as to establish optimal plans for production, distribution, export and import. In addition, blending processes extend to petroleum products, for example, lubricants. A case of the optimization of crude oil blend scheduling is presented. The problem involves a pipeline, 2 receiver tanks, 2 cargo tanks and a pipe still. The table presents the batches of crude oil and the receipt and dispatch orders, including the tanks. The Gantt chart presents the crude oil mix schedule for a 10-day planning horizon. Reducing quality target variance should be at the top of the list for refinery improvements. Deviations from quality targets should be minimized, to charge the pipe still with a steady mixture of crude oil. Steadier quality crude oil mixtures charging the pipe stills will also translate into steadier operations for downstream production units. It also makes good sense to run pipe stills with a constant flow rate for as long as possible. An example of an improved quality target, or key planning proxy is shown in figure. Hypothetical benefit calculations. Total yearly savings in American dollars, quality target variability improvements such as whole crude oil sulfur, 2 million, reduced chemical injection, 100,000, distressed sale of crude oils from the refinery, 325,000, pipeline penalty charge for changes in sequence or timing, 75,000, spot opportunity for crude oil trades, 250,000, and reduced working capital, 100,000. Total year, 2,850,000. These hypothetical benefit calculations translate into over $2.5 million worth of the potential refinery profit that would not have been achieved with manual scheduling alone. It must be emphasized that this number only provides a benchmark or yardstick Pareto, at least qualitatively, the priorities in terms of choosing between other possible and competing capital investment projects at the refinery. From the perspective of overall crude oil costs of the refinery over 1 year, this $2.85 million in savings is less than 0.41% of the total feedstock cost. Success case. Omega, an improved gasoline blending system for Texaco. This case is based on the paper. Omega, an improved gasoline blending system for Texaco, published at Interfaces. In 1980, Omega was used in all Texaco USA refineries and in 2 foreign plants. Texaco estimated Omega's total annual economic profits at more than $30 million in 1980. The image corresponds to the formulation of the omega mathematical model. Oil lubricant blending, a nonlinear optimization problem. Industrial lubricating oil is a liquid or semi-solid lubricant used in various types of automobiles and mechanical equipment to reduce friction and protect machinery and machine parts. It mainly plays the roles of lubrication, auxiliary cooling, rust prevention, cleaning, sealing, and cushioning. At present, the demand for lubricating oil shows a trend of specialization and customization. Different mechanical equipment and applications have different requirements for lubricating oil performance, so there is an urgent need for enterprises to produce specific quality lubricating oil according to the actual demand. Lubricating oil products are prepared by mixing two or more base oils with different properties according to a certain proportion. However, the varieties of base oils refined by oil refining enterprises are limited, so it is necessary to use limited base oils to prepare the required lubricating oils. Therefore, the blending of base oils is the basis for the preparation of lubricating oil products. The most common method of lubricating oil blending is tank blending. The image presents the base oil supply chain. The image presents an oil lubricant production plant. Oil lubricant blend, a nonlinear optimization process. The physical and chemical properties of oil products change when they are blended. The linear or nonlinear relationship between this change and the properties of each blending component is expressed as an additive effect between the components. A certain physical and chemical property equal to the superposition of each component according to its composition ratio is called linear harmony, otherwise, it is called nonlinear harmony. The chemical composition of oil products and additives is very complex, and their physical and chemical properties generally do not have an additive effect, so the blending of lubricating oil is mostly nonlinear. In addition, the performance indexes of lubricating oil mainly include viscosity, freezing point, acid value, flash point, oxidation stability, residual carbon, and so on. Therefore, the optimization of the design of a lubricating oil blending scheme mainly includes two aspects. To select the base oils reasonably to meet the performance index requirements of the blended product, and to establish the blending mathematical model, and determine the blending scheme of each base oil, on the premise of meeting the product performance indexes. The blending formula of early lubricating oil was mainly optimized by the linear programming method. However, many important technical indexes of lubricating oil do not show a simple linear relationship with the content of each component. If the oil products are blended according to the linear programming method, the prediction accuracy of the performance of the blended product will be poor, and unable to meet the actual needs of production. The nonlinear programming method can manage the nonlinear relationship between important indexes of lubricating oil, and the content of each component, and have obtained many accurate prediction models. Then, the blending of lubricating oil is a relatively complicated process. The next model ignores the production technology and the process of lubricating oil, and does not consider the issue of additives. Considering that a certain index of lubricating oil is only related to the corresponding index of the base oil, it is necessary to optimize the design of the blending scheme, so that it meets various performance indexes and, at the same time, is lower in cost. In this paper, a multi-objective optimization model of lubricating oil, based on integer nonlinear programming is presented. The proposed modeling process considers two stages. First, data preprocessing, and second, optimization of the blending. The first is based on predictive analytics and the second on prescriptive analytics. A lubricant blending facility can be conceptualized as a machine that takes multiple base oils, mixes them, and produces multiple types of lubricants. Like Herbert Simon, Hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.